All right, cool. OK, so I'm going to be talking about a new mapping interface that we've been designing. And I'll first point out, my title or my location has changed. I'm now at NVIDIA Research. I was still technically, I think, at Stanford the last time we had this retreat, but I'm working at NVIDIA Research now. I'm mainly funded under the Fast Forward 2 program. So I work on two things in Legion. I mainly support the dynamic dependence analysis that the runtime does, and I also support things like the mapper interface and a lot of things that go on in the high-level runtime. And today I'm going to talk a lot about this aspect of Legion, which is the mapper interface. So the state of our world today is that we write Legion programs, and then we also have this separate mapper interface, which allows you to construct mappers to actually say how to target that program onto particular machines. And the reason that we've gone about this is a very important design decision for Legion. And the reason we've gone about doing it this way is that scheduling is a very, very hard problem that people have to solve. And there are lots of different groups out there trying to solve this problem. Lots of them are building heuristics into their runtime to try and optimize for performance for various applications. And the real important question here is what happens when those heuristics go wrong? And this is the thing that you really got to ask yourself. Because I've spent a lot of time fighting with compilers and runtimes and other porting systems, and every time they do something wrong, there's almost no mechanism for me to actually go through and actually fix what they do wrong. So your compiler is doing instruction scheduling, and it gets the instruction scheduling wrong for some particular machine you want to target. What do you have to do? Well, then you have to go write hand-coded into assembly to actually solve that problem because the compiler is just dumb. Okay, and so the idea in Legion is we want to make this problem not have to have compilers fight our programming system. We actually want to help them solve it themselves. So instead, Legion provides this mapping interface in which we expose all possible decisions which can affect the performance of our code. And the idea here is that programmers can actually specify the important heuristics and decisions for particular applications and machines necessary to get the performance that they actually want. And they have a means through which to remedy if bad choices that maybe our default mapper implementation will make. OK, well, there's some good sides and downsides to this. So first off, the current mapper interface is, let's be very frank, not very clean. And a lot of people have struggled with it up to this point. And I'd like to claim that there's actually a very, very good reason for this. Okay, first off, no one has ever built one of these before. So no one has actually had an interface which allows you to actually specify all possible performance decisions associated with their code and actually compute those things dynamically and not just specify them statically. So Legion comes from a spiritual successor of Sequoia, which actually had a static mapping interface, allowed you to specify mapping decisions statically. And it's much easier to do things in sort of a static world. But if you actually have to write a program to compute mapping decisions, that's a whole other ballgame. So really, we had no idea what we wanted for this mapping interface to look like. So the result was we had a very evolutionary design. And the result today is that the mapping interface is sort of a little bit incoherent. There's lots of things tagged onto different parts of the API. There's lots of different fields that have been added that are very experimental that some people know about, other people don't. And for someone coming to the interface from an unrelated programming system, they often struggle trying to understand what's actually going on in this mapping interface. OK, so now we have some experience actually building this. So we wanted to go back and actually reform this mapping interface to actually allow us to make it a little bit more approachable for people that are first coming to use Legion. So we know mostly what we want. There's going to be some cases where we're going to leave our API open for extension for handling problems that we don't actually know how to solve yet, and I'll talk about that a little bit later. But it's going to be a much more coherent design and much easier to understand and approach. So first off, let's talk a little bit about what the mapper call format is going to look like. So pretty much every mapper call in our mapping interface is going to look like this. You're going to get a mapper call. It's going to be a virtual method inside of our mapper class, just like it is today. But you're only going to have effectively 3 arguments. Your first argument is going to be a reference to the operation that you're actually mapping. So it's going to be a task. It can be explicit region-to-region copy. It could be an inline mapping that you're doing. But you'll get a reference to it. It'll have some metadata associated with that operation. So you better know things like which task you're mapping. You'll have some references that you get about which region requirements you're accessing, all the stuff that you get today. The next argument that you're going to get is you're going to get an implicit or an explicit input structure. And what this will tell you is all the various input fields that the runtime is telling you. This is the information we know about as part of the inputs to this mapping. So you can imagine this task input having stuff like telling you about which instances exist for all the different region requirements in the memory hierarchy that are valid data today. And then the third argument is going to be our output. Effectively, what are your expected to output as a result of this mapper call? You'll notice that we've actually made these inputs and outputs structs, which means that they're going to be open for extension, which means we may add new inputs and outputs to help either allow you to make better mapping decisions in the future by providing new inputs, or give you more control by actually specifying new outputs that you can control. But as we change those things, they're not going to be part of the function signature, such that we won't be breaking backwards compatibility as we add new features to these structs. So the nice thing here is that we're going to get a clear delineation of our inputs and outputs. This is a big complaint that we've gotten from our mapping interface up to this point, is that it's sort of hodgepodge. No one really knows what are the inputs and outputs. It's not very clear. It's going to be much more obvious in the new interface. And I point out already that this is going to be much more extensible. It's going to be very easy to add new things to these input and output structs and allow us to provide new information to people writing mappers, and also get new control over various performance features. OK, so there's another philosophical change to our mapping interface, our new mapping interface, that's worth talking about. So anyone that's actually tried to write a custom mapper for Legion in the past has sort of noticed that we used to do everything around sort of this concept of memories. And so, for example, in a lot of our mappers today, or actually our mapping interface today, when you wanted to specify where you wanted to place your data for, say, region requirements on your tasks, you'd have to say, I want to put it in a sort of a ranking of memories. So, try putting it in my local NUMA domain. If I can't fit it there, put it in my system memory. If I can't fit it there, put it somewhere else. And we did all this with memories as opposed to actually saying the names of the physical instances that we actually wanted to do. And the reason for that, this is actually an artifact of the very, very early days of Legion, before we actually had fields in our programming model. And the result was that, in that case, you only ever really had one instance of a region in a particular memory. So it's very natural to sort of think about doing mapping associated with memories as opposed to actually naming physical instances. But that tends to sort of break down once you start adding fields. And so the idea that we're going to go with in our new mapping interface is that we're actually going to give the mapper a way to name the physical instances that are actually being manipulated as instances of logical regions in the memory hierarchy. Notice these instances are visible to the mapper only. They're not actually visible in the programming model. And this is sort of consistent with our notion of decoupling correctness from performance. The mapper can think about things like physical instances, but they're not actually visible in our programming model itself. And so the mapper is going to have names for physical instances, and this is going to come up in a lot of very different ways, and we're going to look at some of those. One of the most important side effects, though, and I'll point this out right now because it's one of the most important things I want to get across, is that there's not going to be any more guessing about where the runtime actually puts your data. Your mapper is actually going to be able to say which physical instances it wants to use, and you'll be able to know exactly where those physical instances reside in the memory hierarchy. You're not going to have to guess that, did the runtime actually put my instances, which memory did they actually end up putting my instance in that you have to deal with today. That's all going to go away. So some side effects of this is, of course, is that now we're going to have new ways of doing creation and deletion of physical instances. It's going to be a much more explicit thing that your mapper is going to be able to manage. And it's actually going to give you a new way of thinking about how you map your tasks than what you do today. And we'll talk a little bit about that. OK, so the first thing that's worth pointing out is that the way that we're going to manage these instances, now that the mapper is actually going to have names for them, is going to be a little bit different. So mappers are going to be able to hold references to physical instances. So what this means is a lot of people today like to create a few instances that are going to store most of their data for their application, and then reuse those instances over and over again. It's kind of tricky in the current mapping interface because we do everything in memories. You don't actually know that you're reusing the same instance over and over again. But in the new interface, you're actually going to be able to make an instance, hold on to it, and choose to reuse it over and over again, and you won't have to worry about the runtime messing with you. So effectively, what you can do now is you can actually add a reference from your mapper to actually say, I want to keep this instance around so I can reuse it over and over again. So today, instances, as your program is running along, instances sort of are collected by the runtime after one of two things happens. Effectively, once we reference count all of these physical instances that are kept in the various parts of the memory hierarchy. And once all the references are gone, we can actually reclaim that instance. And so there are effectively two kinds of references that we keep around today. One are for pending or executing tasks. If you have a task that's going to use an instance or it's using it right now, you can't collect the instance. Someone's actually using that data. And second, if it contains valid data, and what that means is the most recent copy of a piece of data, we don't actually collect those instances either because we're going to need to possibly reuse it or issue a copy to move that data somewhere else a little later. So that's effectively today's policy for reclamation. As long as you have one of those two kinds of references, you get to keep your instance around. What we're adding now is sort of a third reference, which says the mapper is going to actually say, keep this instance around even if there's no valid data and nobody using it right now, because I know that I'm going to run some stuff later, and I actually want to reuse that physical instance somewhere in memory. Mappers are also going to have some control over deciding when instances are reclaimed. So many people have written custom mappers are familiar with effectively the mapping or mapping fault, which effectively says, or mapping failure, where it says, I tried to map this task, but we didn't have enough resources. I tried to map instances in particular memories, but those memories were full of instances, so I wasn't able to make an instance, and I couldn't actually use it. And today, you sort of have to wait for deferred execution to catch up and let the collector run and actually reclaim some of the physical instances of memory and then actually retry your mapping. But now what we're actually going to allow the programmer to do is to actually, through the mapping interface, allow mappers to do is to actually request that this reclamation happen for physical instances. And actually, we're going to allow mappers to actually choose to rank the sets of instances that they want to have collected in a safe way, such that we don't end up causing your program to break in any way, but we're going to allow you to say, these are extra instances, and I want to actually have those be reclaimed or try to be reclaimed. So there'll be a new mapper call. It's actually going to allow you to decide sort of a ranking of instances that are ready for deletion, and then we'll go through and delete as many as necessary to actually create new instances in that particular memory. So you can think of this as a better way of dealing with resources inside of physical memories as your application is running. Okay. Another side effect of having instances actually. Oh, did you have a question?
Yes, please. Does it mean that runtime parameters like the C size? Thank you. The runtime parameters like C size and those types that sometimes you have to play with in order to prevent those runtime errors that you just described. Does it mean that they will go away? We won't have to.
When you say C size, what are you referring to?
It's this thing that allows you to specify the size of some memory blocks that are going to be used for precisely to create the instances. There are a number of them, right?
Well, we can refer how much data we need based on the logical region specification and the region and the fields that the tasks have requested. So we know how much data we need in terms of space, and it's just a matter of can we actually allocate that space in a particular memory.
Yeah, but I've noticed that at least right now with the way it's working. Now, it seems that the amount of memory that I could figure out in theory that I need actually doesn't correspond to what will cause.
Are you talking about compaction stuff?
Exactly.
Yes, so Sean alluded to that earlier in his last talk. And we're going to deal with compaction as a separate issue. But effectively, compaction will be another one of these options for data layout. I'm not going to talk about it a whole lot today, but because it's a little bit more unclear how we're going to actually do that, but it's something we're thinking about.
Yes, because as a result, a lot of the memory that is no longer to be used will just disappear automatically. It will be garbage collected, right?
But we don't want to do that eagerly though, because we don't know what the next task you're going to run is. And maybe we just haven't seen the task that wants to reuse this particular copy of the data because it's where it wants to be. So there's dangers to it deleting everything right away, which is why this ranking system ranks things to be deleted when you need the space.
Yeah, effectively, coming back to our distinction in Legion of separating policy from mechanism, that would be an example of baking a policy decision into the runtime, and that's exactly the thing that we're trying to avoid, right?
For example, when you do an in situ analysis, right? So you're going to go, so at each in situ analysis step, you're going to recreate the same ancillary structures from scratch. And the behavior that I have seen so far is that new instances, keep piling up.
Sorry, accumulating,
Right.
Right, and that's the reason we're going to give you the ability to choose to delete those things, but we're not going to automatically do it for you.
Okay, but the policy will allow you to specify.
Yes, effectively, the interface will give you the mechanism necessary to decide that policy that you're going to actually do that. Okay, so another side effect of actually having instance names in the mapping API is that we actually have a way now for mappers to actually do a much better description of doing data layout. So Legion is sort of minimally aware of data layout today, but we want to make it much more something that's much more accessible to people writing mapper APIs. So today we have this thing called blocking factor, which allows you to say how different fields inside of a region get laid out. So you can do array of structs. This effectively blocking factor equals 1. You do 1 of field A, 1 of field B, 1 of field A, 1 of field B. You can also do SOA, where you do all the fields of A and then all the fields of B. And then you can do sort of hybrid things where you do 2 of field A, 2 of field B, 2 of field A. But this isn't very good in terms of talking about expressiveness, especially if you think of like you have a 3D grid and you don't know which order you want to lay out different dimensions in and so forth. So there are 2 problems. Effectively, we don't have a sufficient interface today for actually describing data layout. And second, this sort of aspect of data layout isn't actually captured by the task variance that the runtime understands. And as a result, we sort of have a hole in sort of our thing, in one of our properties that we like to guarantee, which is we like to guarantee that mapping decisions can't impact correctness. So today, it's possible for you to actually pick a data layout that doesn't necessarily mesh with a particular task variant that you're going to choose to run, for this particular layout of the regions that you've chosen. And so what we want to do is we actually want to fix that. We want to make sure that we're going to get correctness no matter what mapping decisions you make. So we actually want to make our task variants have to tell the runtime what data layouts they're going to expect. So to do that, we're actually going to need a language to actually describe that. We need something more expressive to describe all these data layouts. So the way that we're going to do this is we're going to introduce a new sort of small set constraint language to describe various properties of data layout. And it'll allow us to describe the layout of physical instances, and it'll also allow us to describe the constraints that task variants are going to assume as part of their execution to know that we need to have data laid out in a certain way in order to use this particular task variant. As a result, we're going to be able to guarantee correctness, and we're also going to be much more expressive to control all sorts of aspects of data layout. So some of the different properties will allow you to describe, and I'm going to give an example of how to do this in a real case on the next slide. We can talk about ordering of dimensions. So if you have a 3D index space, do you want to do x dimension, then y dimension, then z dimension, or do you want a y and then x and then z? You can talk about what order you want fields to be laid out in. So just because your field space has a certain order on your fields doesn't necessarily mean that you want them to be laid out in that order. We're going to allow you to do subdimensions, so splitting x, like x, y, z, into different subdimensions for doing things like tiling. We're going to allow you to say things like alignment. You want certain fields to be aligned on certain byte boundaries. So we'll see an example of why you might want that on the next slide. We can talk about offsets. We can talk about having instances be in certain memory kinds. And as a result, we're going to be able to describe all sorts of things. We can describe basic AOSC order data layouts. We can also describe very basic SOA Fortran order. And we can also do stuff like 2D slices of 3D spaces. And we're actually going to see an example of that on the next slide. OK, so let's actually talk about, do a quick example just to show you some of the constraints and how you can actually use these to describe data layout. Let's say we've got this nice 3D regular grid, X, Y, Z. And every one of these cells, we're going to have 2 fields. And what we want to do is we actually want to do a task that's going to compute a 2D stencil over this 3D array. It's going to need 2 input arrays, or 2 input fields, A and B. And our fields are 8 bytes, pretty simple. And let's say the machine we're running on, we're going to have a task variant that's going to assume we're going to running on a CPU with some AVX instructions. And it'll have a 16 kilobyte L1. So we're actually going to block this thing very efficiently for the machine we're running on. So what are the constraints that we're going to use to specify our data layout for this particular region? Well, the first thing we might want to do is we're actually going to want to block for that L1 cache. So the first constraint that we're probably going to do is we're going to want to make a little 2D slice for us to operate on. So the first thing we'll do is we'll split our x dimension by a factor of 32. So we'll take 32 things of x. And what that'll do is effectively, you can see in the upper left, we're going to start with a very 2D slice in this upper left corner of our 3D space. And we're going to walk through this z dimension. So we split x into a factor of 32. We'll also split the y dimension by a set of 32. So we get a little 32 by 32 slice of our xy space. And then we'll do the next constraint that we'll specify is we'll say that this inner x dimension is going to get laid out before the inner y dimension. So it'll be the most rapidly changing dimension. So we can walk through x and then walk through y. And this will sort of be how we're linearizing these dimensions in memory. So these will be laid out. This 2D tile will be laid out contiguously in memory. The next thing that we'll say is that we actually want to have the inner y dimension come before what we call the field dimension, which are our set of fields inside of our logical region. So what this means is we're going to do a 32 by 32 slice of A and then a 32 by 32 slice of B in memory. So you can think of this as being linearized. We'll get a 32 by 32 chunk of A, a 32 by 32 chunk of B. And the reason we choose to do this is because effectively this 32 by 32 slice times 8 bytes times 2 fields gets us our 16 kilobytes. So we're blocking exactly for that L1 cache. So we're going to have there are 2 slices of A and B, and we're going to be able to do that 2D stencil over both of those while they're still in the cache. And then we can move on to the next set of 2D slices for both A and B. So we have to say that the A field is going to come before B. This isn't quite so important. We probably could have left this constraint out if we wanted to. Next, we say that our field dimension is going to come before the z dimension. So what that means is that we're going to do the next dimension that's going to be changing is the z dimension. So we're going to walk through the z dimension for these 2D slices, so we can walk through memory. And then we can say stuff like z comes before outer x, and outer x comes before outer y. And that gives us like our next sets of slices. So we can do the next set of 2D slices in the upper right. Then we can do 2D slices in the lower left and walk them through our z dimension. And finally, because we're doing AVX instructions, we actually want to say that we're actually going to want the inner x dimension to be aligned on a 32-byte boundary. The reason for that is we're going to want to get nice, dense SSC or AVX vector loads. And so those have to be aligned on a 32-byte boundary, so you get the fast version. And so this constraint language allows you to specify all these properties of how we're going to do data layout for a particular physical instance of our logical regions. It's going to give you, a very, very expressive way for describing data layout so you can get really, really good performance. OK. Another question we get a lot about this new interface is, why bother describing all this in so much detail? Well, I think there's a lot of power in it. And the power that we're getting is that really, Legion is going to have all the DMA code internally. In fact, this is actually down inside of the realm part of Legion. But we do a lot of effort. We go through a lot of effort to make sure that our DMA code is actually very, very optimized and capable of doing all these different layout transformations. So if you were to do all this today, you as a partner have to do all this by hand. You'd have to write all the code to move everything into this layout. You have to write all the code to use this layout. And then you have to write all the code to transform this to whatever layout is coming after this. And effectively, we've taken away 2 of those 3 things. Now all you have to do is worry about the code that actually uses this layout. And Legion's going to take care of transforming it on the way in and on the way out, and doing so in a way that's very, very, very efficient. And so we're actually going to get, we're actually making it much easier for you to explore the space of performance optimizations by changing your data layout without you having to worry about writing all that code to do all the different DMA operations to move data in and out. OK. I want to talk about a couple other aspects of how these instances actually are having multiple instances in the mapping API actually changes things. So this is an example of a problem that we actually have today in the current mapping API, is that we can't really satisfy mapping or region requirements with multiple instances. You have to make a single instance in order to satisfy a region requirement for your tasks. And the result is that we end up having to make copies. So we might have one task that's writing field A, and another task that's writing field B, and a third task that's consuming both fields A and B. Today we have to make separate, if each of these 2 first tasks make separate instances, this third task is going to have to make a third instance. And we're going to have to issue copies in order to update the data in this new instance. This is really unnecessary. Really what we should do is actually say, task 3 should be able to reuse, if it wants to, the previous 2 instances that were already generated by the 2 tasks before it. We actually want to get rid of those copies. But in order to do that, we actually have to satisfy a region requirement with multiple instances. So this new mapping API is going to allow you to say, OK, I actually want task 3 to use 2 separate physical instances for this one region requirement, and actually be able to have access to be able to reuse those existing instances instead of having to make new ones. It's important to call out, well, that'll get rid of our copies. So all those unnecessary copies that you get today are going to end up going away. It's important to point out that this really only works with SOA-style layouts. So your constraint language is going to have to say, you want an SOA-style layout. That's actually not such a bad performance price to pay. If you actually wanted AOS, then we actually do have to do the copy, because we're going to have to do the reordering of our data to get A and B fields, or red and blue fields interleaved to actually make sure you get the locality that you want. So it's up to you, what your task variant is going to assume. But if your task variant says I only need sort of an SOA-style layout, we'll actually allow you to reuse those instances and use multiple instances to satisfy region requirements instead of forcing you to make copies unnecessarily. Another thing that's going to change is we're actually going to allow you to put multiple region requirements in the same physical instance to actually allow you to say, satisfy a region requirement with the same instance. This is really important performance optimization and code productivity optimization. So borrowing some syntax from Region earlier this morning, you might have some fields that store pointers that point into multiple logical regions. This pointer could point into either region R1 or R2. Today, we have to put those in separate instances, and what you have to do is you have to write some code that looks like this. It effectively says, I don't know which region my pointer is pointing into, so do a little safe cast to test. If it's in R1, we can dereference it out of the first region, and if not, we can dereference it in the second region. This is actually pretty slow, because now you're doing sort of these checks on all the different pointer dereferences. So what we're going to do is actually allow the new mapping interface to actually say, put both of these regions in a big sort of common region that contains both val data for both regions. And now we can actually not have to do all those safe casts. We actually do a dereference into this one big instance instead of having to dereference separately into the two separate regions. So we get our standard pointer dereference. Well, you might ask a question is, how do we guarantee correctness when you do this? Just like specifying the layouts for our actual region requirements, we also want to specify that a task variant may be assuming that both of these two logical regions are going to be in the same physical instance. So we actually need a way to specify that so we can guarantee correctness without having a mapping decision break correctness. So what we're going to do is we're also going to have a second another sort of set constraint language to actually describe the assumptions that task variants have on their execution. So just like we had a set constraint language for describing the layout of our logical regions, we're going to have a set constraint language for describing the assumptions that tasks make about their execution. So you can use the set constraint language to describe very basic things like what are the assumptions on my ISA? Am I assuming x86, PowerPC, ARM, PTX, whatever you want. You can also assume stuff about the resources that you're going to consume, stuff like cache sizes and registers. But most importantly, you can also have these things called co-location constraints, which says, I expect that these two region requirements are going to be located in the same physical instance, such that we can guarantee that's going to be abided by the particular mapping that the mapping API chooses. So we'll have the other thing that comes with this is that now we're actually going to have you specify these constraints when you go to register your tasks. So every time you register a new task variant for your tasks, you're going to have to specify all of your layout constraints that are assumed by your task. And you'll also get to specify all the constraints on what assumptions you're making about the hardware you're targeting, how many resources you expect, what co-location constraints you have, and so forth. We're also going to allow you to do this dynamically. Today, we force you to register tasks statically, but in a world that we're moving to with DLLs and JIT, we're actually going to want you to allow you to register tasks dynamically. So you'll notice that even though today we require you to statically register tasks, we'll allow you to dynamically register tasks in the future. So mapping tasks is actually now a little bit different than it is today. So in the future, the way we're going to do mapping of tasks is going to be slightly different. So the first thing we'll do is we'll pick a processor that we're going to run on. The next thing we'll do is we'll actually name physical instances for all the region requirements that we're going to use. And once we've done that, we sort of have a decision to make. Our mapper can either choose to pick a task variant that it's going to actually use when it goes to run. And if it does that, the runtime is actually going to be able to use its knowledge of the layouts of the physical instances that the mapper has chosen, as well as the constraints that were registered with that particular task variant to verify that all the constraints are satisfied. It means that you haven't broken correctness. If it doesn't satisfy the constraints, we'll actually report that back to you. And the alternative case is the mapper can actually be a little bit lazy about this. We actually know what the constraints are for using various task variants. We can actually pick a variant that runs, that most closely satisfies the constraints based on the instances and the processor that the mapper has chosen. So, effectively, now we're giving you a little bit of a decision. You can either be lazy and let the runtime pick for you based on what task variants exist, or you can, say, I want to use this one, and we'll check to make sure that you're actually going to be correct. And if not, we'll let you know. The important thing here is that correctness is guaranteed no matter what you do. So on the second case here, you can ask yourself a question. What happens if you can't find a task variant that satisfies all the constraints based on the processor you've chosen and the physical instances and their layouts that you've specified? Well, sort of today we have one effective question, or one sort of way to solve this, which is we report a mapping failure, and you get to go back around this whole loop, and you can pick some new instances with different layouts, and hopefully you find a task variant that is actually satisfied. But there's actually an alternative answer that you can imagine wanting to be able to do, and as you actually maybe want to generate a new variant that's going to satisfy all these constraints that you're going to be requesting for this particular processor and data layouts. So one of the directions this new mapper API is going to allow you to do is actually to register what we call task variant generators with the Legion runtime. And what this task variant generator is just a function. And the idea is it's going to be invoked by the runtime to generate a new piece of code, a new task variant for a particular functional task specification. And what we'll do is, you can register one of these task variant generators for every logical task ID that you specify in your application. And what you can do now is, every time we find we don't have a task variant to satisfy certain constraints, we'll invoke this task variant generator. we'll pass in the processor that you chose. We'll also pass in all the instances that were chosen and all their layout constraint information. And this task variant generator can spit out a new task variant that says, this is the variant that you should actually use for this particular chosen processor and layouts. This task variant generator can also spit out some information. It can spit out some constraints that say, these are the task constraints under which you can use this variant or reuse this task variant. And it'll also specify additional constraints on the layout under which you can reuse this task variant. So the runtime can now cache this task variant in a table and remember all the constraints that are necessary for using this task variant and allow you to reuse it over and over again in the future. And yeah, these constraints are what dictate the runtime's ability to reuse these task variants. Now, we also, when you register these task variants, we're also going to allow you to register a little bit of static data associated with them that are inputs to this task variant generator. And the way you should think of these is that really these are just, this might be some intermediate representation of this task that says, this is the input that describes the functional code for this task. And my task variant generator knows how to, take this along with the constraints and generate a new functional equivalent, new task variant for the runtime to use. So what is this, task variant generators really? Well, I think the way you should think about them is that this is just a generic interface for doing dynamic compilation with any compiler. Effectively, the Legion runtime doesn't need to know what's in that static data block. It doesn't need to know what's in the task variant generator. You can have any compiler in there. You can have any intermediate representation in there that you want. And the runtime knows that this is just an interface for dealing with code, with dynamic generation of code. So you can put your DSL in there. You can put region in there. You can put Clang or LLVM in there. You can do whatever you want to generate code, and this is going to be the interface that Legion's going to use to sort of speak to any compiler that's going to be dynamically invoked. OK, I'm going to skip these next two slides. I'll leave them out there for people that want to talk about them offline. You guys can look at them offline, but sort of a little bit of a detail of the new mapping API. I do want to talk about this part. One of the other aspects of our new mapping interface that we're adding is the ability to dynamically manipulate the dependence graphs that the runtime is generating. So we have sequential semantics, and Legion is dynamically building a dependence graph, and it's dynamically discovering as much parallelism as possible inside of this application. But just because we discover that doesn't actually mean that you actually want to exploit all that parallelism. Oftentimes it's better to actually take advantage of stuff like locality and actually reduce your parallelism to get better locality so you can get better performance. So the answer, whether or not to do this is always, it depends. Again, this is a policy decision that we want our mappers to be able to control. So we want to make it a mapper decision as to decide, how much of this parallelism that Legion is actually discovering should we actually exploit. And so what we want to do is actually allow our mappers to manipulate these dependence graphs to actually do so in a way that doesn't break correctness, but allows you to actually do performance optimizations. So one of the first things that you can imagine doing with these dependence graphs is actually starting to fuse tasks together. So Legion might actually discover that there's parallelism amongst tasks, but you actually want to fuse some of them together for various reasons. So we can actually fuse them to leverage locality, or we can fuse them to reduce analysis costs. And we can do this in the mapper interface because we're going to want to make these decisions based on the machine we're targeting and the shape of the graph that we're looking at, the dependence graph that we're looking at. So first, a couple examples. These are just sort of cartoons, but they should give you a feel for the kinds of things you can do. So first, you might have two tasks that have a data dependence between them. You might want to fuse these things together. And when we say fuse, this isn't like fusing the way the compiler would fuse and actually do code transformations. In the Legion runtime speak, fusing just means run these tasks back to back on the same processor. So run task A and then run task B consecutively so that you get nice cache locality and other properties, and you get to amortize the analysis of both those two tasks. We can also fuse tasks for locality. So say that we have a green task here that generates an output, and that output goes to both the red and the blue task. We might want to fuse the red and the blue task together such that they run back to back so they can leverage the same input in the same memory. And third, we might have completely independent tasks that we actually want to fuse together just to reduce the cost of the dynamic analysis that Legion is doing. So we might have two completely separate tasks that we fuse together to reduce analysis costs. Another transformation that we can imagine doing on this dynamic dependence graph is actually replicating tasks. So sometimes you actually can increase parallelism and actually do redundant computation to actually allow you to reduce the amount of communication that has to happen. And this allows us to get more parallelism. It also means that we have to do less data movement. And this can actually work to our benefit both within nodes and across nodes. So let me give you two examples. So one of the things that we can actually do with this, one of the examples that we saw in S3D is actually, we have sort of this pattern. We have this computation called calc_y_difflux. It has a bunch of different tasks that consume the output of calc_y_difflux. Calc_y_difflux generates a lot of data. And it does so, and it's very expensive to move that data inside of your machine. But what you want to do is possibly run your calc species and your calc tau tasks on different processors. In particular, I might want to run one of those on the CPU and one of them on the GPU. But I don't want to have to pay the cost of moving that data from calc_y_difflux across the PCIe bus. So instead what I want to do is I want to actually run calc_y_difflux twice, once on the CPU, once on the GPU, have it generate the data on both sides of the PCIe bus in parallel, and then have my consumers actually consume that data without having to actually move it. So this is an example of actually doing redundant computation to reduce communication. In a world where communication is very, very expensive, doing redundant computation is almost, is going to be a big win in a lot of cases. Another example that we've sort of been playing around with has sort of been a motivating factor for multi-node replication of tasks is thinking about something like multi-grid, where you might have, you're doing a V-cycle, you're going up your hierarchy and coming back down. And the coarse grain part of your V-cycle, things get very, very small and very minimal computation actually going on. And instead of having to send all your data to one place and having that one node have to blast the results back out to all your nodes, you might actually want to replicate that coarse grain computation across multiple different nodes, such that when you go to send your data back out, all those different nodes that have replicated that computation can send to a subset of the machine, and you get much better parallel communication going on. So anyway, we're going to actually give you some interfaces for actually playing around with these sorts of ways of manipulating the dynamic dependence graph. There's a lot of uncertainty on how this is going to work, so the API is going to be a little bit flexible at first, but we're going to be looking for people to actually try it out and actually play around with it. Let's see. One of the important things that we're also going to be doing associated with this new mapper interface is actually we're going to be working on a new default mapper. So the default mapper today is actually something that is sort of stayed on the side of the Legion project, and we've been able to sort of hide behind this aspect of we let you do your mappings automatically, so we haven't actually worked at all the heuristics that a lot of the other runtimes are working on to actually make their code fast. So we realized we actually want to bulk up our default mapper, make it a little bit more robust, actually work on optimizing it to actually get some pretty good heuristics in there. So we're going to add some heuristics for doing better management of data, doing some load balancing, and better algorithms for actually constructing other mappers from our default mapper. So you should be seeing sort of a new default mapper come with a new mapping API. It'll be sort of lagging behind. It'll take some time for us to develop it. I'll also point out that we're working on our default mapper in a new mapping language that we are calling Bishop. So just like the Legion API is in C++ and it's a little bit verbose, our C++ mapping API is also verbose. So you can imagine, just like Region is sort of a nice productivity layer on top of the Legion API, Bishop is going to be a language for actually writing mappers. I'm not going to dive into this too much today, but the idea is you write a Bishop program, the Bishop compiler will compile it and generate out for you a Legion mapper that satisfies the mapping API. Wanchan has promised me that it's going to be sort of an experimental part of our exercises tomorrow, so for those of you that are sticking around tomorrow, you'll actually get a chance to play around with that. And my last slide before lunch, because I'm sure everyone is hungry. This new mapping API is going to be rolling out probably sometime in January. While it's going to come around and it's going to be sort of a new interface for everyone to start playing with, I want to point out that it's not going to be fixed in any way. It's still going to be very much open for modifications. There are lots of open questions that we still have with this mapper API. What are the best ways for dealing with deferred execution? How do we compose multiple mappers for applications that have libraries that are composing together? What are the best practices for building mapper data structures? What are good abstractions for doing mapper construction? These are all things that we're sort of thinking about and sort of tooling around, but until people actually start building some more of these things, we're going to leave them on the drawing board and allow our interface to sort of be able to grow to accommodate sort of what we sort of notice as are becoming good practices for building these mappers. So with that, that's the end of my slide. I'm happy to take any questions. I can also take questions offline if anyone wants to ask them there.
How is this going to coexist with the existing? Is it going to be one or the other? You switch it off one day? Or?
That's a good question. So I think the plan is, so we've actually done a couple of iterations on the mapper interface, and each time we built sort of a shim that would translate from the new mapping interface back to the old one. So what you could do is you could run an old mapper through the shim on top of the new mapping interface. and I think we'll probably try to do something like that. Let's see, it depends on how people feel about it, but I'll probably at least write a shim to allow people to do an easy migration, but eventually it'll flip over one day, but there'll still be a shim there that you can inherit from the old one, and it'll just be like changing one inheritance line in your mapper.
One thing I'll point out is that in pretty much all the custom mappers we've written right now for applications, they tend to be fairly small. So the effort involved in switching it to a new API, especially one that makes it more concise, is actually possibly easier than teaching it to use a shim.
Same for the partitioning API that's currently existing right now, the coloring API, how the backwards compatibility will be with your new additions.
Well, so yeah, there will be backwards compatibility. It won't be terribly pretty, but basically the idea is if you hand a coloring to Regent, we will create a new field. We'll copy all the contents of the coloring into the field and then hand it off to the new partitioning logic. So it'll be about as fast as it was before. And you won't get any of the benefit of dependent partitioning, but you have the old functionality.